Hey chemistry friends, Mrs. Hanson once again. Since I've sent the last test review video out, I received a few emails with additional questions, and I thought I would share them with all of you via video. So here I'm calling this my buffer, titration, and additional aspects of Equilibria test review session 2, and I have about 8 different problems. Let's take a look at the first example, and I have this question specifically as I notice it's a trend when we have stoichiometry to consider in a titration. So let's take a look at number 2, our first example. We have a 50 ml sample of an aqueous solution of sulfuric acid. Let me just tabulate what we have for the acid, H2SO4. And we're titrating that with a solution of sodium hydroxide, NaOH. Right off, I notice that we are titrating a strong acid with a strong base. A strong versus strong, so that I know pH is determined by the excess reagent. Ka or Kb when we have strong versus strong. So it's just the molarity of the excess reagent that is determining the pH. So that's a little note I have here. Strong versus strong, no equilibrium. 100% of the titration pushes to the right. But notice we have a diprotic acid, H2SO4, and we have just one equivalence of the base ion, OH negative. If I just finish the reaction out, the salt that forms based on ionic charges is sodium sulfate, Na2SO4, and of course HOH, which is water. But the key here is in balancing the equation. Clearly we see that 2 equivalents of the base, 2 units of OH are necessary to neutralize a diprotic acid. So the stoichiometry here is important, critical to realize that it takes twice the number of moles of base to neutralize that diprotic acid, sulfuric, H2SO4. Let's tabulate what we were given underneath. We were given 50 mils of H2SO4, and it is 0.375 molar of base. And we are at 62.5 mils of the base. And it says we are at the equivalence point. The concentration of sulfuric acid is, so we're looking for the molarity of sulfuric acid. What is the molarity of the acid, knowing that we are at the equivalence point? So just remind yourself, at equivalence point means you have a stoichiometric ratio where you have the perfect mole ratio 1 to 2, 1 mole of acid, 2 moles of base. In other words, there's no limiting or excess reagent, 1 mole of acid for every 2 moles of base. So think about this as our given, and this is what we want to calculate. We can just use straightforward solution stoichiometry or unit cancellation to derive our answer. Starting with what we were given, we had 0.375 moles of NaOH in every liter of solution. I mean, that's the definition of molarity, is moles per liter. And we titrated out a volume of 62.5 mLs. Since I have a mole per liter, I will put in 0.0625 liters, just so my units then cancel. So my molarity times volume has really converted. Just to kind of think about that, molarity times volume in a liter is the mole. And that's what I've done. And I can just set that over a 1 so it looks pleasing to the eye. We've taken molarity of the base, multiplied it by the volume of the base, and we're at the mole. Now in our stoichiometry, we have to consider that every 1 mole of acid requires 2 moles of base. If I'm going to make a mistake in this, it's right here. It's forgetting that I need 1/2 the mole of sulfuric acid as compared to sodium hydroxide to reach the equivalence point. We've converted in our first step. Notice how we've canceled out liters of the NaOH and we're left with mole. In our next conversion, we canceled moles of NaOH and now we're at moles of acid. Recall that we want to solve for the molarity, which is moles per liter. So with our next conversion, what we'll end up doing is taking the volume, the 50 mils that we titrated, I'll use that as a liter, and I'm going to put that underneath as a divide by so that I can get molarity. Moles per liter is molarity. 1 mole of acid requires 2 moles of base in this equation. So let's hit this out all in one big step. I have 0.375 moles of NaOH times 0.0625 liters of NaOH. I'm going to then divide that by 2, which is multiplying by 1/2. And then I'm also going to divide by 0.05 liters of acid, H2SO4. And when I'm finished with this solution stoichiometry problem, I find 0.234 molar sulfuric acid solution. I want to just emphasize, often we think this equation will carry us through always. Molarity and volume of acid equal molarity and volume of base. But this is only true if the coefficients are 1-to-1. In this case, clearly it was not a 1-to-1 ratio. So we had to consider the stoichiometry as we prepared the answer. MV equal MV is not the formula to use for an acid-base titration of strong versus strong unless it is a 1-to-1 ratio. So thinking about MV equal MV, an example might be HCl and sodium hydroxide. That's a 1-to-1 ratio. This equation would work. Or let's say HNO3, a strong versus strong. MV equal MV would work because these are monoprotic acids. But don't forget that the balanced equation is critical to consider in your titration problems, because if you have anything else, any other stoichiometric ratio other than 1-to-1, don't forget you need the stoichiometric ratio step before you finish the problem. Okay, good work. Let's look at a next example. Oh, there's nothing on that screen. Here it is. This is a question about an indicator. What is the best colored indicator to use in a titration between the weak acid called acetic acid with the strong base called NaOH, and why? Well, let's consider the chemistry here, and that's the important thing is we have this weak acid called acetic acid. Now this is the organic formula, CH3COOH. There's acetic acid. Sometimes we write it as HC2H3O2. So just to kind of realize these are both the same formula for acetic acid. And when you get into organic chemistry, you'll recognize this Cu as the carboxylic acid functional group. This tends to be the organic nomenclature for acetic acid, and this tends to be the inorganic nomenclature, putting the hydrogen first. So just recognize acetic acid written either way. So the chemistry is going to take this weak acid called acetic acid and titrate it with a strong base. And it clearly says you're at the equivalence point. So you know that you'll make sodium acetate and water, right? Acid-base chemistry, a salt and water is produced. You also know that at the equivalence point, right, that's what an indicator does, is turn color when the base moles have equaled the acid moles, that if these two are indeed consumed, the only thing present in the solution to affect the pH is the sodium acetate. We know that the cation of a strong base will not affect the pH, right? Its parent is a strong base, so no effect on pH. However, the anion of a weak acid will hydrolyze to create a solution of high pH. Let's take a look why. When acetate is formed, right, sodium acetate. Acetate is the anion of a weak acid. We know it will hydrolyze to produce its conjugate and the hydroxide ion. So at the end point, we've learned of a weak acid plus strong base, the end point is going to be slightly basic. And in our notes, we even drew that curve, right? We said if you start with a weak acid, you kind of have this pH that kind of resists change, and then you'll see it come up. But at the equivalence point, if you look here, this is not 7. It's probably about 9 or so because you made a basic solution. When a weak acid is titrated with a strong base, I know the endpoint will produce an anion that hydrolyzes to create a basic ion. So right away, I already know my answer. It's the only choice of indicator that's in the basic range for the endpoint. I can also do this mathematically. Notice this equation here is a base chemistry, right? Basic. So I would need something called a pKb to describe the hydrolysis of acetate. So if I take this pKb, which I can find by negative log of 5 to the 1, and when I hit that out, I find that to be, let me hit that quick, 9.26. So this expression that we just wrote about the hydrolysis is 9.26. Again, another verification that phenolphthalein would be the best indicator because it also turns color at a point of 9.2. So if, let's just say, if I had more choices in a base range, I would still want to select the one that's closest to 9.2 since that's going to be the pKb of that reaction. So you can do this logically, knowing that a strong base with weak acid hydrolyzes to produce a basic solution at the endpoint, and the phenolphthalein is the only base range indicator I have. Or you can do it mathematically by changing the pKb, and I knew to use pKb because it's basic. And therefore, I could also select, based on my answer, the indicator closest to 9.26. Okay, good work. Here's a question. Again, it can be a thought question. It doesn't necessarily involve math at all. Simply like the last one. Of the following solutions, which has the greatest buffering capacity? Well, as I look at this list, I notice they all contain the same ingredients. They're all the weak acid called acetic acid and its conjugate base, acetate, knowing that sodium is a spectator. Sodium is a cation from a strong base, so no effect on pH. But this is a buffered solution because I have a weak acid and its conjugate base. So what does buffering capacity mean? Well, it simply means which one of these pairs is going to be able to handle strong acid or strong base as it's poured into this solution. The greater the buffering capacity, the greater the concentration available to neutralize the addition of a strong acid or a strong base to help it resist a change in pH. Think of this really as a bar chart. Here I have 0.8 molar of the acid and 0.7 molar of the base. I have a large quantity that I could add acid or base into this buffered solution, and I know that I would have a greatest amount of capacity to neutralize the strong addition of acid or base. If I think about this, I have 0.5 versus 0.2. I'm trying to draw this shorter than the one I drew above. Here I have even shorter, 0.3, and this is 0.4. I have, a little bit, 0.1 versus a little bit, 0.1. The greatest capacity is the greatest concentration. It's that easy. They're all the same ingredients. To have the greatest buffering capacity, choose the highest concentration, the largest molarity, so that you have plenty of buffer to neutralize the addition of acid or base into the system. Cool. All right. Oh, a solubility problem. This one, as I analyzed quiz results, I see about 4 or 5 times this one was missed. Let's go through this one together. It says, what is the molar solubility of manganese hydroxide, MnOH taken twice? And of course, we see that it will ionize into an aqueous ion of manganese and 2 aqueous ions of hydroxide. So just dissociation of that salt. It tells me that the KSP is equal to 1.9 times 10 to the negative 13. If I wanted to know the molar If I wanted to know the molar solubility in just pure water, I would set this to x, this to 2x, and solve for the value of x, right? So let's say in pure water, I would solve the KSP problem by saying, remember just to write out that the manganese ion concentration times the hydroxide ion concentration squared. The squared comes from this coefficient. So I would let manganese be x, I would let hydroxide be 2x, and I'd have to remember to square it. So this comes out to be 4x cubed for KSP. So plugging this in, 1.9 times 10 to the negative 13 is equal to 4x cubed. Let me solve for x. 1.9 times 10 to the negative 13 divided by 4 and then cube root. So I use that raised to the power of 1/3 to take the cube root. And the x comes out to be 3.62 times 10 to the negative 5th molar units. This is in pure water. But the problem said we're not in pure water. We've buffered it to a pH of 8.00. Now think of this as a common ion problem. If I'm buffering a solution to pH of 8, it's the same as saying the pOH is 14 minus 8, which is 6.00. And I can say that the hydroxide ion concentration then would be 10 raised to the negative POH. So the concentration of hydroxide is 1 times 10 to the negative 6 molar units. This is the common ion concentration of hydroxide. So now when I consider my original equation, when this, oops, I did Mg, it's Mn, manganese, MnOH taken twice, when it dissociates, we said a moment ago, I have X and 2X in pure water, but now in the buffered solution, I'm adding an additional quantity of the hydroxide, which we said was 1.0 times 10 to the negative 6 molar units. And I clearly remember saying this 2X is so small that it's negligible in comparison to the quantity of this common ion that we might as well toss it out. So the KSP now becomes, which was, here it is, 1.9 times 10 to the negative 13. The value of Mn still is X. The value of hydroxide, now instead of 2X, as if it were in pure water, instead we use the buffered solution concentration of hydroxide, and remember to square it. I'm tossing out the 2X because it's so small. So now when I solve for X, the molar solubility, 1.9 E negative 13 divided by 1 times 10 to the negative 6th squared, and my calculator reads 0.19 molar units. Clearly we see that by buffering the solution, the hydroxide ion concentration changed, and therefore the molar solubility has also changed. All right, so that one allowed us to kind of tie in pH into a common ion effect. I had to turn pH into POH to find the concentration of hydroxide, the common ion in that dissociation. Cool. Let's look at another together, one that was emailed. Again, a topic on buffers. Which one of the following cannot be mixed together to form a buffer? And I know a buffer is a weak acid and its conjugate base, or a base, a weak base, and its conjugate acid. So those are the criteria to be a buffered solution. In KOH, letter A, with HI, do you notice that both of these are strong? Yeah, so right off the bat, a strong base with a strong acid. If I even add these together, a strong versus strong, 100% forms products. I'd have potassium iodide and water. Acid base makes salt and water. Clearly, I do not see conjugate pairs, so this is not a buffered solution. Now, in this example, I found my answer right at letter A, but if it's all right, I'd like to talk more about why the others do work, because not all of them look like conjugate pairs. Let me say, for example, letter B. I have sodium hypochlorite and nitric acid. Again, just think about exchanging the positive ions. You produce HClO and NaNO3. Sodium hypochlorite is the conjugate base of this weak acid. So here's the weak acid, here's its conjugate base. So yes, that is a buffered solution. We meet the criteria of forming a buffer. In letter C, we have NH2CH3, methylamine is what that's called, reacting with HCl. Now notice the nitrogen. This is an ammonia derivative. The nitrogen has the ability to form a positive ion. So the hydrogen adds to the nitrogen and it forms a plus charge and leaving the chloride. So you had this proton transfer, acid-base, Bronsted-Lowry acid-base chemistry. So in that proton transfer, here are the two conjugate pairs. You have a weak base and its conjugate acid. So yes, this forms a buffered solution. Letter D is exactly the same chemistry. Notice the nitrogen. The nitrogen in the first has no hydrogen attached to it, but in the second it does. So we've had a proton transfer. This is a weak base and its conjugate acid. So yes, that is a buffered solution. And here we have acetic acid placed into a strong base, sodium hydroxide. Oops, forgot my A in there. And of course, we exchange the place of the positives, so we would make NaC2H3O2, sodium acetate, and a water. Well, I can see this is a weak acid, and here is its conjugate base. A weak acid, acetic acid, and the salt there, sodium acetate, is its conjugate base. So yes, this is a buffered solution. But there's no way to do the chemistry to create a weak acid and its anion or a weak base with its cation when we start with strong versus strong. So letter A does not work. This one was sent to me via email as well, and it goes back to the very first problem we worked together. I'm mixing a solution of magnesium hydroxide, which is a base, with a solution of hydrochloric acid, HCl. What is the pH of a solution by preparing 40 mils of magnesium hydroxide at 0.125 molar, and I've added 150 mils of a 0.125 molar acid solution. So again, we have a strong versus strong titration. We know if we were at the equivalence point, pH is 7. But that's only true at the equivalence point. If we're not at equivalence point, it is determined by the excess reagent. Right? And so we would need to know the pH as the negative log of the molarity of hydrogen ion. All right, so that's our goal. Well, let's see what we have to start with. 40 times 0.125 is 5. So I have 5 millimoles of the base, and 150 times 0.125 is 18.75 millimoles. Now this is my caution. Always start with a balanced equation. What do you notice? EQUATION. What do you notice? We have a 2 equivalent base, 2 groups of hydroxide with a monoprotic acid. When I finish my equation, I can see that magnesium chloride and 2 units of water would form when I balance that equation. Clearly, we see that 2 moles of the acid are necessary to balance that base with its 2 groups of hydroxide. We need 2 H's to balance 2 OH's, making 2 waters. So this is the trick again, is the stoichiometry. I know this is the limiting reagent. I know that it will be consumed and run out. But there is a 1 to 2 ratio. When 5 millimoles of the base are used up, 2 moles of acid are consumed. So I'm actually using 10 millimoles of the acid to reach the endpoint here. And that leaves me 8.75 millimoles of excess acid. If I'm going to make a mistake in this problem, it's forgetting to remember this is a 1 to 2 stoichiometry. For every 1 mole of base, I need 2 moles of acid. For every 5 moles of base, I'm going to use 10 moles of acid. The 8.75 millimoles of the acid over the new combined volume, which is 150 plus 40. We have a total of 190 mLs when I'm done adding those two solutions together. 8.75 over a combined volume of 190 gives me a concentration of 0.046 molar units of the acid. We have what we need to find pH. pH of a strong acid is found directly from knowing its concentration, 0.046 molar units. So in this reaction, negative log of the excess molarity of the acid, negative log of 0.046, and my calculator is reading 1.34. Pause as you need to for think time. I'll work one more with you in this review session. Which of the following aqueous solutions would you expect AgBr to have the lowest solubility? Well, let's think about what it's asking. We have AgBr in dynamic equilibrium, with its aqueous ions. The molar solubility increases as you push to the right. So the more soluble, so I'll write this, increasing molar solubility favors the forward direction, right? The more ions in solution, the more soluble the salt is. And if you push to the left, you are decreasing molar solubility. You are pulling ions out of solution. This becomes nothing more than an application of Le Chatelier's principle. So when I look at letter A says I'm going to add 0.1 molar of silver nitrate. Well, you see the common ion? If I add 0.1 molar silver nitrate, I'm increasing the silver concentration, which would then force the solution left, decreases the molar solubility. This is not one that would increase the solubility, it's going to decrease. It's pushing left. Letter B is pure water. Well, with pure water, there's no common ion, so you're going to push to the right? If you think about AgBr plus adding water, you're going to push the equation to the right. That's increasing solubility. LiBr, well, here's the stress there. Adding Br pushes to the left. Adding letter D, adding Br also pushes to the left. And again, letter D is adding Br to push to the left. So we have letter A, C, D, and E all pushing the dynamic equilibrium back to the left, decreasing. Which one of them is going to have the greatest effect? Well, it's as easy as saying, well, if they're all pushing left, the one that's going to put in the most common ion will decrease the solubility the most? And that's our answer. It's that easy. The highest molarity of the common ion pushes the reaction to the left furthest and would decrease the solubility of AgBr the most. Okay, so here's just a quick review of some samples. Keep the emails coming if you'd like. Have a great day.